Start. So today we are going to talk about allotropes. We were doing actually allotropes which were shown by carbon, right? We have already covered diamond and graphite. The third category of the allotropes of carbon is a very special one, which is fluorines, and it has till now we have three type of fluorines which have been discovered, right? Which have been made. So let's talk about that. See, when we are saying this thing, so what happens is actually the fluorines, they are actually the C60 fluorine, that is okay, C60. Yeah, this one is the Buckminster fluorine, right? And it's basically a soccer shaped molecule having alternately like hexagon, pentagon, hexagon, pentagon. So we have around 20 hexagons and 12 pentagons in the structure of one molecule of this C60 fluorine, right? And you would believe that this is like what happens. One carbon is attached to three more carbon atoms. Okay. If I make the structure like this, so this carbon is being attached with three more carbon atoms at one time. Okay, so what happens is the structure is not planar, right? It is not a planar structure. So what happens is it gives us a kind of thing like it's a kind of, you can say a cage like thing, a round cage, something like that. So here we have delocalized electrons. So remember this thing that fluorines, Buckminster fluorine has got delocalized electron. I hope you remember the concept of delocalized electrons. What was that? Matlab, what were they actually? Delocalized electrons. What do you mean by that?
Is it when the electrons they are coming out, there's like an extra one, so it helps in electrical conductivity?
Yep. You are correct. So be confident about that. So delocalize, as the word says, they're not stick. They're not sticking to one position. Localize means they are to be found at one particular place, right? But when we are adding the word the D means they don't want to stick to one place. They keep on moving. So delocalized electrons effect is surely to be found in Buckminster fluorine, but the case is that they are less reactive as compared to graphite, because graphite has got the maximum delocalized electron effect, right? So when we talk about the reactivity, this Buckminster fluorine is less reactive when we compare it with the another allotrope of carbon, which is graphite, right? Okay. So another fluorines which we have, that is C70. Okay, that means it has got 70 carbon atoms attached in one molecule. Okay, and another one is C84. Okay, so actually what happens is uh, when we have two graphite electrodes and we set up an electric circuit, and electric discharge is being passed on, but we take up helium gas at a low pressure. So what happens, the graphite, it starts evaporating. Okay, the graphite is, it is undergoing evaporation, and after evaporation it undergoes condensation. The evaporation process is followed by condensation, which results in the formation of soot, which is actually unburnt carbon particle, right? Now, this soot is dissolvable or soluble in organic solvents like benzene, toluene. These are organic solvents, right? And when we separate them out from the organic solvents, we get yellow brown color, right? And this is basically your fluorines. So how we have prepared fluorines? We just took helium at low pressure, and graphite electrodes are there. Electric discharge is being set up. After that, the process of evaporating the graphite starts, followed by condensation of graphite, leading to the formation of that soot. This soot is basically your Buckminster fluorine. Okay, so another a new allotrope of carbon is being made artificially. It's a synthetic material which is called carbon nanotubes. Okay, this is a new thing on in the market, which is carbon nanotube. Okay, this is another allotrope of carbon. Okay, a lot of studies are being done on this, and you know that these are basically the carbon nanotubes. Na? When we talk of what are they actually? We take very small, very thin sheets of graphite and make cylinders. Like we roll them into cylinders. Like for example, if I take a paper, right, and I start rolling that, right? Suppose this is a paper. If I'll roll this, it will become like this, right? So these are basically rolled cylinders of very thin graphite sheets. But the key point is they're very strong and they have unexceptionally high electrical conductivity. So what advantage they have? First, they are very strong, right? Second, very high electrical conductivity, right? So diameter is typically around 1.3 nanometers with a length of up to 1 centimeter. So if we talk about a molecule, that is quite big in size. Okay. So let's move on. So the next investigation, what you have to do, you have to differentiate between the properties of allotropes of carbon. And I think you can do that in a tabular form, right? And when you're doing the tabular form method, you just what key points you have to note. First is the structure. The first point should be of the structure. Explain the structure, then make the diagram. Next, you have to see, like compare the trend in the melting point. Then if the particular allotrope is a conductor of electricity or not, then Buckminster will be conductor of electricity or not. We have to consider this thing. And then Buckminster fluorine is soluble in cyclohexane. Now, cyclohexane is another organic solvent because of the pure form of soot. It tends to get dissolved in organic solvent, but graphite and diamond, they are not because they do not undergo evaporation and condensation, right? So now we are going to see allotropes, which are shown by some other elements, right? This was graphite. Okay, fine. That is done. See, they have given us some hints also. The things which you had to do in your project work, that is already given in the book on the next page. So you can compare the properties. Add-on point will be you can make the diagram of the structures. You can talk about the concept of delocalized electrons. That would give an added feature to your tabular differences. Okay. Now, the allotropes, like allotropism, which is shown by some other elements, they are phosphorus, sulfur, and oxygen. So let's talk about that. First of all, we are going to make space for them. Okay. So the first element which we are going to pick will be phosphorus. Okay. Phosphorus is an element which is showing us allotropism, and there are three allotropes of phosphorus. Okay, there are three allotropes of phosphorus. One is your white, then you have red, and then you have black. Okay, red, white, red, and black. Right? Let's move on. Now, you know that phosphorus is a non-metal. Okay, phosphorus is a non-metal and it is very reactive non-metal. It is one of the most reactive non-metals. Okay. And you know one thing, non-metals, they do not react with water. Okay. Non-metals, they do not react with water. And this property, we utilize them in case of phosphorus. Because if I keep phosphorus in air, in open air, so it will start burning. Right. So what we do, we keep phosphorus in water so that it does not react with oxygen. Now, see, the phosphorus which we were keeping in water is actually your white phosphorus. Okay, now how I have remembered, water and white both start with W. Okay, so by this way, I remember the white phosphorus has to be kept in water in order to be, make that phosphorus kept for a longer time. And white phosphorus out of these three allotropes is the most reactive. Okay, it is the most reactive. Actually, what happens? there are like phosphorus ki, the atomicity of phosphorus is 4. P4 molecules, they are packed up and the resultant shape is a crystal shape. Okay, so there are like one phosphorus atom will be attached with three other phosphorus atoms so as to be in a very definite shape. Okay, so white phosphorus is found in the crystal form, right? This is phosphorus. It is going to be bounded by three more phosphorus. Okay, now this, then they'll have some lone pair also. This way, this phosphorus is also attached with three more, right? Then this. So this phosphorus is also attached with three, and this phosphorus is also attached with three. So it is giving us a very stable structure, crystalline structure, and it is very reactive in nature. When we talk about the red phosphorus, in red phosphorus, na, it is a kind of chain-like arrangement. Okay, red phosphorus has got chain-like arrangement of again P4 unit of molecules. Okay, so there is like what happens when one P, then here, right? Again. Now what happens? This P is going to bind up with another packet of P4. Okay, so there is an open bond which is found between the two units, leading to a chain-like structure. Now, this type of structure is very stable, okay, as compared to the P4, na, individual P4 units, so it will be more stable, right? So, red phosphorus, the structure of this chain-like arrangement is comparatively more stable, right, leading to less reactivity. So red phosphorus is less reactive in nature as compared to the white phosphorus. Okay? Yeah. Next comes your black phosphorus. Black phosphorus is actually the most stable phosphorus form. Okay? It is the most stable allotrop. Up in this, the layers of phosphorus atoms are there. So they have very strong, covalent bonding between the phosphorus atoms, which is there in between the sheets. And between sheets, it will be only weak forces. So this structure is very stable. And because of the increased stability, further there is reduction in the reactivity. So they are the least reactive. Okay. So when I'm talking about the white phosphorus was the most reactive, right? And the presence of valence electrons added to its reactivity. Then we had red phosphorus. The structure was a linear arrangement of phosphorus molecules, but in that case, the structure was stable as comparatively to the white phosphorus, but still the reactivity it further decreased. And when we are talking about the black one, it has got the most stable structure, but yes, it is the least reactive in nature. Is that clear?
Yes.
Okay. So next element, which is going to show allotropism, is your sulfur. Okay. I'll write over here the next. Okay, I'm going to pick blue. Right. The next element is your sulfur, right? Who is showing us allotropism, and it has got again three type of allotropes. One is your rhombic, then it has monoclinic, and the third one is plastic. Okay, now when we talk about rhombic and monoclinic sulfur, na, in this case, the 8 sulfur atoms, they are attached with single covalent bonding, forming a ring-like structure, right? So it's a very beautiful structure. If I say S, right, again S, then it's a kind of wave-like thing, right? One wave is joined, right? And this will be the common one. So this is a kind of M you're forming if you just see this thing. So there are covalent bonding, and it's a kind of ring-like structure. So these molecules, they are, arranged in different crystals. So the difference will be there that the arrangement of molecules will be slightly different in rhombic and monoclinic allotropes. But the difference in their properties is not that much. So because they're undergoing the same kind of chemical reactions. But the third one, the third, which is your plastic sulfur, that is a long chain of sulfur atoms, which are having the single bond. So they are attached like this. Okay, single molecule. So this type of the chain arrangement of sulfur gives that a non-crystalline texture or a rubbery texture. Okay, but if we keep this thing as it is for a long period of time, it is going to change into ring-like structure. Okay, this plastic is going to change into ring-like structure on standing for a long time. Is that clear?
Yes.
Next comes your oxygen. Now we are going to take green. Okay. Okay, oxygen has got two allotropes. One is your simple diatomic oxygen molecule, and the other is triatomic oxygen molecule. This is simple oxygen, oxygen gas, which we breathe in. And this one is O3 is your ozone. Okay, this is a poisonous gas, and the oxygen which we breathe, it has a boiling point of minus 183 degrees Celsius. Okay, and when we talk about the ozone, it has got minus 111 degree Celsius. Okay, so this is at the higher boiling point. Okay, so these so we have around four elements which are showing allotropism: carbon, phosphorus, sulfur, and oxygen. And you have to remember each and every allotrope of every element. Okay. Now, see, if I talk about the physical properties of elements and their structure, so what we conclude from that? See, noble gases, they exist as monoatomic elements or molecules, right? They have only the thing which keep them, bind together, that is only dispersion forces. And you remember, dispersion forces are weak in nature. So that's the reason, because the bonding force is weak, so boiling points are very low. So they have even very low melting points also, because of involvement of very weak forces of attraction. For example, I talk about helium, so I just write like this, na, helium, right? Argon, right? Neon. So these are noble gases having only one atom in their molecule, and hence they are called monoatomic. Or you can say atomicity of noble gases is one. Okay, right. Next is when you have diatomic molecules, right? Diatomic molecules, for example, hydrogen, then you have chlorine, we have oxygen, we have nitrogen. So in this, the atomicity of molecules is 2. So that means we have 2 atoms in one molecule. Now here we have the forces which keep them, together. The force of attraction which was there. Again, it's weak dispersion forces. But as the molecules get bigger, matlab the electronic number is increasing. So the dispersion forces, they are getting more stronger. Okay, and iodine being like it's a solid, and next is bromine, which is your liquid. So these gases have their boiling points a little bit higher side, right? Because of more stronger dispersion forces. Okay, so here, if I talk about the diatomic molecules, the intramolecular forces. Okay, the intramolecular means when in one molecule, this hydrogen and hydrogen, they are binding together, right? In this case, the intramolecular force is also very strong. So it is very difficult to break that bond, leading to their higher boiling point as compared to the monoatomic molecules. Now, phosphorus and sulfur, they exist as polyatomic. Phosphorus, atomicity of phosphorus is 4 and atomicity of sulfur is 8, right? So these molecules are very large, obviously. So dispersion forces, they are stronger if I compare them with monoatomic or diatomic molecules. And hence they are solid at room temperature. Now, elements like carbon. Now, carbon, it forms covalent lattices. Okay. And thus, the strong chemical bonding is throughout the crystal. Okay. So, that's the reason why they have high melting point. Okay. So, the forces which are there, bonding, the strong chemical bonding is to be found all over the crystal. And hence, more force is required to break that crystal. And hence, the melting point is high. Okay. Okay. So, elements which are metals, right, and their physical properties, like they are very lustrous, they are good conductors of electricity. They can be, beaten into sheets. They can be drawn into wires. So, what's that? Actually, it's a lattice structure. There are like the base will be formed by the positive ions, and there will be delocalized electrons that is immersed in that. Positive ions are immersed in that. So, melting point for metals are considerably high, but we cannot explain the trend based on their structure. We cannot, because of the impact of delocalized electrons. It has got a very solid delocalized electron effect. Then some elements are like which are known as semi-metals, right? Like boron, silicon, germanium. So the like their structures although respond to that crystal covalent lattices, but their bonding jo hai na, it is relatively easily excited into a delocalized one, right? As if we are talking about metals. So they have got both the things, the properties of non-metals as well as the properties of metals. So melting point is reflected by their covalent lattice structure, whereas the luster which is present in them, that is determined by the delocalized electron effect. Is that clear? So now we know about the allotropism. We have compared the properties. We have seen which elements are showing us allotropism. So let's move on and see what's next. This was the chapter. So we have finished our chapter, and I think you're able to make up the things now. So we'll see. Okay. So here you have again the assignment, and I think you can do that, review questions. Okay, clear. Let me check if there is something which you can. In this question number 14, you have to make a graph representing the things. Okay. So try to do these if in case you face any problem. So we can discuss in the next class, right? Okay. So this one is your module, properties, structure of matter. Okay.